So I do want us to consider this part, which is the use of our matrices in the simplification. We can be given questions. I want you to refer back to questions such as drawing of the image, okay? To draw the image of a certain triangle ABC. If you are to relate what we had before, let's say it is a translation, okay? You're asked to draw the image of triangle ABC. If it is a translation, they are going to specify that it is a translation, and also note that they are going to give you the translation vector. You'll be given the translation vector, so you can draw the image by movement. You obtain full marks for that. Or you can draw the image by calculation. I talked about the methods that you can use there. That was for a translation. On a reflection, we had a certain similar, it was just a similar consideration that we used. But only that we do not have a vector under a reflection. What is important on a reflection is the mirror line. The equation of the mirror line. The mirror line. That is the most important thing. So you had to draw the images, or you're drawing the image of whatever that you're given the mirror line, which is the equation of the mirror line. You were given the equation of the mirror line. You're given that equation. You considered the issue of the distance. I specify that. We talked about that. Maybe it's the line of y is equal to x. There's a triangle that you're given, A, B, C. You can transform this A to the mirror line, the distance, you form 90 degrees, you mark your point B, same to the mirror line, the last part, and C also you mark, then you can even join to have your triangle. We talked about that. The concept of drawing the image given the object and the mirror line. Draw something that you can just have it on the graph. Done. You can do it on the graph. But now you're saying, instead of doing these constructions that we do understand from the properties of a reflection, you know the properties of a reflection, you are using the properties to reverse the description. Now you are drawing the image the same way that you had before. Object and image, you describe it as a reflection, equation of mirror line. So if it is that consideration that you're describing now, you are drawing the image. So I talked about those methods. That method actually of moving by doing the constructions, you move accordingly. The distance to the mirror line must be the same distance that you're going to move from the mirror line, forming a 90 degrees. I talked about that. If the line is a vertical, you just move straight from the point to the mirror line, you move straight along to the image. Same as if your line is a horizontal line, the distance to the mirror line, same distance, you move straight from the mirror line going down. So if this is A, this will be the image of A. If this is A, this will be the image of A. If this is A, this will be the image of A if a line is like this. If you're given a vertical line, it's just moving straight. A horizontal line, you just move straight to the horizontal line, back to the, to the image in the other way. Understanding that the object is on the other side, image on the other side of the mirror line. Object on the other side, image on the other side of the mirror line. object on the other side of the mirror line, the image on the other side of the mirror line. We cannot have the object A and its image A on the same side. No, it's impossible. The image has to be on the other side of the mirror line that we are given. We talked about that method. I'm very sure that you worked on that. Now we are saying, instead of us using these constructions or adjustments, we can use matrices. Or sometimes they will actually force us to use a matrix. So you need to understand now where the part of the matrices is used in this transformation. So it follows that whenever a matrix of a transformation is used, so we do not have a matrix for translation. I talked about that. Translation, it has a vector, so there's no matrix there. The matrices, we're going to talk about reflection, rotation, and all other transformations. If you watch other videos, I think you saw the matrices explained for other transformations. So I'm saying that it follows that in whatever transformation that you're going to have, whether it's a reflection, it's a rotation, the matrix of that transformation, when it multiplies the coordinates of the object, or when it multiplies our object, we are supposed to obtain the image. The matrix of the transformation that you are using, it's a rotation, it's a reflection, it's a shear, it's a stretch, enlargement, whatever that you're given. The matrix of that transformation, because this can also be given in paper one. So you must understand that idea now. A matrix times object is supposed to give us the image. Matrix times object. So if there is a center now, so you're supposed to note this. If there is a center, if there is, so let's say there is a given center. Okay. So whenever you are given a center, this matrix that you're, this condition that we are saying matrix times object is equal to image, it can only be applied when the center is 0, 0. So this condition can only be applied, if the center is 0, 0. If the center is 0, 0. That is about the origin. When the center is 0, 0, it means about what? About the origin. About the origin. So what if the center now is not 0, 0? This condition can only be applied if center is 0, 0. So if the center is not, you are supposed to make adjustments so that the center is brought back to 0, 0. And you use this consideration or this condition of a matrix times object giving us the image. So there are adjustments to be made if the center is not 0, 0. So we're going to talk about that if the center is not 0, 0. So this condition that we are seeing here, to use this condition, you use it when the center is 0, provided that there's a center on that. And where there's a center, you're going to expect these adjustments that I'm talking about on two transformations, a rotation. Remember when we talked about a rotation, there's a center there. So this can be used on a rotation when you are talking about the center. On a reflection, there's nothing about a center there. You just take your matrix as it is. There are no adjustments. On a shear, there are no adjustments. There is no center. There is invariant line. So we do not consider that. So it's a rotation and the enlargement. Enlargement, remember, when you describe an enlargement, if you check on the other videos, I talked about that. An enlargement, you state that it is an enlargement. You state the center of enlargement and the scale factor. So as you can see on describing an enlargement, there is a center there. So the transformations, all transformations that you describe, including the center in the description, whenever you're describing that transformation, there is a center included into this in the description. These are the transformations that are going to be affected by this condition of the center. All other transformations, except for translation, because translation, the matrix is not even there. So talking about the remaining one, which ones are remaining? Reflection, the shear, and the stretch, one-way stretch and two-way stretch. These transformations that we are seeing here, they are not affected by the center. They do not have the center on the description. We never talked about the center. So these ones, they are not affected by the center. So in these transformations, the reflection, the shear, the stretch, the center is not there. So it is just direct. You just use your condition. Matrix times object is equal to image, direct. There is nothing special that you're going to do, that you're going to subtract the center, this and that. Now the center is not, there's nothing like the center is. You just take your matrix as it is, you multiply it to the coordinates of the object, you obtain the image. So the question now is, what are the matrices that we are going to use under a reflection, under a rotation? For shear, stretch, and enlargement, check the other videos on shear, enlargement. I talked about those matrices. So make sure that you do so to watch those videos so that we understand this together. So I'm just going to talk about how do you find the matrices now for a reflection and a rotation. It's true that you are supposed to know these matrices just to say it's a rotation, but consider also where these matrices were taken from. I explained that in order for us to have a matrix for a certain transformation, we must consider what we refer to as the unity square. The unity square of our Cartesian plane. Remember our Cartesian plane, it is showing us x and y values from the origin, 1, 2, minus 1, minus 2, 1, 2, minus 1, minus 2. So what we refer to as the unity scale of our, the unity square is taken from the part of how the scale is given according to the x and y. Remember, you'll be saying 2 centimeters represent 1 unit, 2 centimeters. So we are referring to this part here, 1 and 1, the first square. So what is important about this square are the ones that we are talking about, the first value and this value. These are the ones that we are going to focus with, these two numbers. So with these two numbers, we are just going to ask ourselves everything about the transformation, the one that you want to obtain, its matrix. Okay, let's say we have got a reflection here. This is our unity square, this one, I talked about it. So for a reflection, we have got this. This is our reflection. The matrices that we are going to have under a reflection is for the line y is equal to 0. The line y is equal to 0 is our x x-axis. So we are simply talking about the x-axis. That is, we are going to need its matrix. Number two, the line of x is equal to 0. The line x is equal to 0 is the y-axis. So we are going to need its matrix. These are the important lines in your syllabus that they are going to ask you for their matrices. The line y is equal to x. And number 4, the line y is equal to minus x. So these are the only transformation, the only mirror lines where this method of the matrix method can be used. So it means if now you are given to transform triangle ABC onto triangle A1, B1, C1 under a reflection, and the equation of the mirror line is y is equal to x plus 1. We cannot use these matrices for now in our syllabus. This is now for the advanced level. In your syllabus, you're not going to do that. You do not have a matrix so far that can represent this. So what is the only way? What is the way out now? The only way out is now using that idea that we talked about in the previous class. Drawing of the line y is equal to x plus 1. Drawing the line of y is equal to x plus 1. With the line of y is equal to x plus 1, let's say this is what we have. You can now transform the shape that you are given. Maybe it's a square, whatever that you're given. You now transform to the what? To the image by drawing. You have to use that method. So, not to say this part here, we cannot use that. We can use, because remember we had, when we were talking about reflection, we actually reflected some other shapes along the line y is equal to 0, if you still remember. Along the line x is, and we're doing it by what? By calculation. By the construction. But you're actually transforming, okay, along the x-axis, you're moving the point to the x, then you move the same distance to the image, to the x, same distance to the image, you count to the x, then you draw. Remember how you were constructing from our previous class. So this time now, we are saying, let us use the matrix method in place of these. So these are the 4 mirror lines that you need, their matrices. So like I said, you need to know how to determine the matrix from the unity square. So it follows that, remember the idea of a reflection. If you reflect a point here along this line, the point is going to move the distance to the mirror line, same distance to the what? To the image. That is the idea of the mirror line. So, in creating these matrices, you are going to simply ask yourself to say, this point is 1. Remember the coordinates, it was supposed to be 1, 0 like this. But we are talking about a matrix of the format 1, 0, 0, 1 something. The format is no longer like 1, 0 or 0, 1 like this. It's not a matrix. These are coordinates. So we can also have it that way to say, instead of writing this as 1, 0 like this, let us write it in a matrix way. Let us write it in a matrix way. Is it possible 1, 0 like it's a point 1, 0? So how do I write it in a matrix? In a matrix, I'm supposed to have something like this, 1, 0 like this, x, y. So we can write this as 1, 0. Minus 1, 0 again, minus 1, 0 like this. So it's going to be written as what? Minus 1, 0 as a matrix. So this is minus 1, 0. Okay, let's move on to the minus 1 in the y and the 1 in the y. This one, there's a 1 here. So this 1 in the y, remember, if a point is given here as 1, What does it mean? If a point is given there as a 1 here, there's a point here given as a 1. The coordinates of the point in the y-axis is the x is 0 this time. Y is 1, so it's 0, 1. The coordinate is supposed to be 0, 1, 0, 1 in the y-axis. If the point is at 2, 0, 2, so this, instead of us writing it just like 1, we can write it in matrix way. 0, 1, it means 0, 1 like this as a matrix. So in the y-axis, that will be 0, 1 like this. The same as the minus 1. The x there is 0, y is minus 1. So this can be written as 0, minus 1 like this. So it means this point minus 1, we can write it as 0, minus 1. So this is just rewriting these in a matrix manner. So after rewriting this now in matrix manner, this is what you're going to do. Remember, you want to create these matrices, or in case you just have to memorize, if you do not want to go through this, you just have to memorize. But you don't even need to. If you understand this unity square, put the unity square in your head. You can even see what is happening if you. There's no need for you to write it down. But this is where these matrices were taken from. So you transform the x point first, followed by the y. You transform the point that is in the x-axis, our reference point on the unity square. So you transform the point in the x-axis first according to the transformation that you're given. Then you move on to the point in the y-axis, also according to the transformation that you are given. So always you start with the point in the x. So this is your starting point. Then you end with the point in the y. Always, always. Okay, so let's have this one. We need the matrix of a reflection in the line y is equal to 0. The line y is equal to 0 is our x-axis. Y is equal to 0. So like I said, always you start to transform the point in the x-axis. So now you ask this, you ask yourself this. If I am to transform this point 1, 0 here under a reflection, knowing the properties of a reflection, and the mirror line is in the x-axis, this is where the mirror is. The mirror is in the x-axis. Where are we going to have the point 1, 0 on the image? Where are we going to have it? Where? No, it's going to remain there because it lies on the mirror line. Remember the concept that when you're drawing the image, if a point lies on the mirror line, the other points can be transformed to their images, but this point lying on the mirror line cannot be drawn anyway. It will remain on the mirror line. It is invariant. So meaning to say our x, which is our starting point, it's on the x-axis, which is our mirror line. It lies on the mirror line. It lies on the invariant line. So it will remain as it is. So that's 1, 0. You write it in a matrix way. Always, I said, you start with the point in x, then you end with the point in y. So let's move on to this point in y. If we transform this point 0, 1, this one, we are still in the line y, we are still under a reflection. So if we transform the point 0, 1, this one, under a reflection in this x-axis, you are transforming along the x-axis. You are transforming this point. Where are you going to have it at the end if you transform this point 0, 1? Along the x-axis. This point is going to move. Remember, this is a horizontal line. What I said, it is going to move same distance to the mirror line because the x-axis is the mirror line. And what is it going to do? It is going to move same distance to the image. So if this was 1, it is going to move on to -1. And what is the point there? It's 0, -1. So you now write it as a matrix 0, -1. So the image of 0, 1 along the x-axis is 0, minus 1. You are transforming along the x, so the image is going to be this side under a reflection. The transformation there is under a reflection. So the same thing, if our mirror line this time is the y-axis, the starting point is not, the starting point does not change. Whether it's a stretch, any transformation, you start here on the x. You start at 1, 0. So you transform it. So if we are to transform the point 1, 0, this time our mirror line is what? Is the y-axis. This is our y-axis. This is our mirror line. So if I am to transform this along the y-axis, what is going to happen? It will move one distance to the mirror line and one distance to the what? To the image. It is going to move because the mirror line is a vertical line, so it moves straight to the mirror line, to the image. So to the image, what are we having at the image? That's minus 1, 0. You write it down. Minus 1, 0. That's how you create the matrix. Minus 1, 0. You're done with the starting point, which is x. You move on to the end point, which is y. If you transform this point here, 0, 1, in the y-axis, this one, it is in the y-axis. So you transform it in the y-axis as it is by a reflection in the y-axis. Where are we going to have the image? If our y-axis, this one, which is the line of x is equal, is our mirror line, where are we going to have it? Nowhere. It is going to remain there. It is on the mirror line. It lies on the invariant line, so it will remain as 0. Just like what we saw on the point 1, 0, this one. It lies on the x-axis, which is our mirror line. So when you transform this point, it is going to remain there. There is no shift that is going to happen because it is on the mirror. So this is the matrix for a reflection for x is equal to 0 or for the y-axis. This is the matrix of a reflection for the line y is equal to 0 or for the x-axis. So you can even create these matrices. Let's consider y is equal to x. By now, I understand that you have an idea because we talked about this line previously. I said this is the line which divides your Cartesian plane into two equal parts like this. Having a positive gradient, it has a positive. Remember, all these lines like this, they have got a positive gradient. But this one, it is a special line. It divides our Cartesian plane into two equal parts. This part here and this part here will be two equal parts. So, using the transformation technique, that if a line is like this, the way that I move to the mirror, remember, you move to the mirror line, you form a 90 degrees to the image. Remember how you were doing this? It is the same technique that you're going to use to form the matrix of this reflection in the line y is equal to x. But as usual, you're going to start with a point which is in the x-axis. So ask yourself this question. If I am to transform this point in the x-axis along this mirror line of y is equal to x, what is going to happen? Where am I going to have its image? The point is here. I want to know the image. So remember how you're doing. You're moving to the mirror line, forming a 90 degrees, then you move to the what? To the image. So if we are at 1, 0 here, guys, and you form a 90 degrees, we can't form a 90 degrees going this direction, no. We are going to form our 90 degrees to the other side of the image. If the object is this side, this is where the object is. The image is going to be on the other side of the line, y is equal to x. So if we have got a point 1, 0 and it is transformed to the other side, we are going to end with this point of 1, 0 now at what? Now at 0, 1. That is where we are going to end. So this will be a 0, 1. The same thing, remember always, you start with the point in x, then you start with the point in y. You started with this one, x, you reflected it. You move on to the point in y. This is our point in y, which is 0, 1. If you transform this point is 0, 1 along the line y is equal to x, where do you expect to have It is just a reverse of 1, 0. Remember, you transformed 1, 0, and it was what? At 0, 1. So if you transform 0, 1, it's going to back to what? To 1, 0. Because it's going to move one distance to the mirror. Then one distance going down. Where are you going? At 1, 0. So this matrix at the end can be given as 0, 1, 1, 0. Just like that. 0, 1, 1, 0. So this is for the line y is equal to x. The same sense that we are using here is the one that we must apply if this is now of y is equal to minus x. So if the line is now of y is equal to minus x, with the idea that we have, this is a line which divides also our Cartesian plane into two equal parts. But this one, it has a negative gradient. This is the line of y is equal to minus x. We saw the one of y is equal to x passes like this with a positive gradient. So using the line of y is equal to minus x, this is now our mirror line, y is equal to minus x. So what will be our matrix for this line of y is equal to minus x? How are you going to have it? So you just ask yourself, always remember we start with the point in the what? In the x. The point in the x is 1, 0 here. So if we transform this point along this mirror line, where is it going to end? So remember, the point must move a certain distance to the mirror. So it's going to move one distance to the mirror line. It forms 90 degrees. When it forms 90 degrees, where are you going to have it? We are going to have it at the end at what? At 0, minus 1. There are no points like 0, minus 2. No, it's just, guys, 0, minus 1, 0, 1, 1, 0, or minus 1, 0. Okay. So this is where you're going to end it. That's a reflection in the line of y is equal to minus x. So the point is going to end at 0, minus 1. So you're going to do the same thing with the point that is in the y-axis, which is our end point. Remember, you start with the x, you end with the point in the y. So if you transform this point in the y, which is 0, 1, along the line of y is equal to minus x, where are we going to have it at the end? So it will move a certain distance to the mirror line, forms a 90 degrees to the what? To its image. Same distance, 1 unit to the mirror line, 1 unit going downward. So where are you going to end? You're going to end at what? At minus 1, at minus 1, 0. So that's minus 1, 0. The point now written as matrix. So these are the transformations that you're going to use whenever a reflection is considered where a matrix is to be applied, or where you need to apply a matrix. It must be one of these conditions or one of these mirror lines. So like I said, if the mirror line is now y is equal to x plus 1, forget about this method. Opt for your usual way, or the traditional way of our calculations when it's like that. So these are the matrices of a reflection. A reflection. So you must memorize this. I don't know how are you going to do it. Me, I don't know. So once you have this matrix, now it follows matrix times object is equal to image. Now we move on to the rotation, just in the same manner of our unity square. For a rotation this time, you are going to expect a condition of your matrices under a rotation 90 degrees clockwise. So remember, I said for a 90 degrees clockwise, it is the same. Whenever you talk about a 90 degrees clockwise, it is a minus 90 degrees. So it is the same as the other way of anti-clockwise, which is referred to as a positive angle, 270. So a 90 degrees clockwise is the same as a 270 degrees anti-clockwise. So in the same manner, if you understand this, it follows a 90 degrees anti-clockwise it is going to be simply opposed now by what? What it is equal to 270 degrees clockwise. It was anti here, so here it will be a clockwise. So as you can see, it opposes 90 clockwise, 270 anti. 90 anti-clockwise, 270 it just opposes when it is coming to 270. 180 degrees, we cannot say there is 180 clockwise or 180 anti-clockwise. 180 is just 180. You're going to end at the same point for a 180 anti-clockwise or for a 180 clockwise. Also, 360 degrees, yes. 360, remember, that's if you transform a point 360 degrees, it will end up where it was. It will end up at the original position. So they are not going to ask you a consideration of a 360 degrees because the object will end where it is originally. So this is your rotation. So in each case, we will need each matrix that you need to know, take it by heart, just like for a reflection. Everything taken from our unity square. Remember what I said. You consider this according to the transformation taking place. It is a rotation. So remember we said this is 1, but we can write as 1, 0. This is -1, but we can write as -1, 0. This is 0, -1. This is 1, which is 0, 1. And I said always you are supposed to start with a point in the x. Using the idea of the rotation, the transformation that you're given, it's a rotation 90 degrees clockwise. What does it mean? This point is going to move 90 degrees clockwise. Remember, always you start with a point in the x and you end with a point in the y. So if you are to rotate this point 90 degrees going in the clockwise, the way the clock moves clockwise like this, where are you going to end? If you rotate this 90 degrees clockwise, we are going to end at what? At 0, -1. The end point, you are now writing your answer. That is a matrix now, at 0, -1. You are done with the point in the x, your starting point. You move on to the point in y, which is your end point. If you rotate, you're asking yourself, if you rotate this point 90 degrees clockwise, where are you going to? You rotate it 90 degrees clockwise. It is going to end at what? At 1, 0. So in the same manner, this is the transform, this is the matrix again. We said 1, 0. This is the matrix of a 270 degrees anti-clockwise. Meaning to say, if a 270 degrees anti-clockwise is asked, they are talking about that, or they're asking you about that, you can use it from a 90 degrees clockwise, the one that you are used to. Because you are not used to this 270, but it's just one and the same. All right, let's move on to another one. 90 degrees anti-clockwise or 270 degrees clockwise. So we are talking about 90 degrees anti-clockwise, starting with this point 1, 0 here. We want to start here. So this time it is rotating 90 degrees anti-clockwise like this. This is the anti-clockwise way. So from where it is, if it rotates 90 degrees anti-clockwise, where are we going to end? We are going to end at 0, 1. Remember, this is already 90 degrees, but we are going anti-clockwise. So we are going to end up at what? At 0, 1. We now write our matrix. So this is 0, 1. This is the point in the x, our starting point. We do the same thing about our ending point, which is the point in the y. Always, you start with x, then the point y. So if we rotate this point 0, 1, 90 degrees anti-clockwise, where are we going to have our image? If you rotate this point 0, 1, where are you going to have? You are rotating anti-clockwise. So we're going to end up at what? At -1, 0, 90 degrees. So this point where it is, that's -1, 0. That's the matrix. So whenever you are given a rotation, whenever you are working with a rotation, 90 degrees anti-clockwise. This is the matrix that you're supposed to have at the end. Okay? So like I said, is either you're going to memorize or you know how to have this, I don't know. But you need to know all your matrices. 180 degrees also. So 180, guys, is just a straight line. So if you rotate, remember we start with the point in X. So if you rotate this point in X, 180 degrees is going to be 90, 180. So it will end up at what? At minus 10. Whether you move it this way, 90, 180, it will end up at minus 10. The same thing with the point with the point in the Y. If you rotate this 180 degrees, 90, 180, it will end up at what? At 0, minus 1. Whether you go this way, 180, 90, 180, it end up at what? At 0, minus 1. So this is the matrix that you're going to use for rotation, 180 degrees. For a reflection, for a rotation of 360 degrees, 360, guys, you are simply back to the... If you rotate the point 10, because this is your starting point, you start with 10 always. So you rotate the point 10, 360 degrees. Where are you going to have it? It is going to return there where it was. If you rotate the point of 1, 360 degrees, it will remain where it was at 1. That's your normal identity matrix. Remember, this is a special type. It's not just a normal matrix. It's called what? An identity matrix. All right? Remember that 1001. 1001. So, as you can see that a rotation under the description of a rotation, there was a center. So whenever you are going to use any one of these matrices, except for 360, 360, guys, it will be there. It means that these matrices must be used when the center is 0, 0. Because there's a center there. Remember what I said on those transformations where a center is used. We said it's a rotation and enlargement. And on that case, if the center is not 0, 0, I said we are going to make adjustments. But for now, just to use matrix times object is equal to image, the center must be 0, 0. Center must be 0, 0. Center that you're given there must be 0, 0. So we have typical questions where we need to use these matrices. So I'm going to explain with examples in our next class. So I think with this, guys, there's a lot that I explained. I'm going to talk about examples in the next video. So make sure that you watch it, where I'm going to explain about the use now of matrices, multiplying to get the object, to get the image. But like I said, this is the condition. For a reflection, you just take straightforward matrix times object is equal to image. There are no adjustment. There is no center under a reflection. It's just the issue of what? Of the mirror line. So there it's straightforward. Matrix times object is equal to image. So you can even try to do questions that we did from the previous exercise on a reflection when you are drawing the image. So this is what you do. You take if there was a mirror line for the x-axis, you take the matrix for your x, you multiply to the coordinates of the object, you get the image. But we're going to talk about that in our next class. Just after this one, we're going to talk about that using graphical presentations. Then there's no center. So this formula is straightforward. And these are the only mirror lines where this matrix can be, or these matrices can be used. They can be used on these mirror lines only. Any other mirror line, x is equal to 1, y is equal to 2, any other mirror line, you have to consider exactly how you transform an object to its image. There is no matrix there. Don't expect to use any matrix. So be careful on that part. We're going to talk about those examples, but be careful on that part. Then a rotation, just like an enlargement, Because there is a center, these matrices are going to be used if the center is 0, 0. If the center is not 0, 0, adjustments have to be taken. So we're going to talk about that also. So do yourself a favor, revise as much. Know these matrices by heart. Know how to construct these matrices in case you've forgotten your matrices, so that we can be able to apply them in our next class. Till we meet again.